Well, we saved one of the most important aspects of Hohokam society for last, looking at the water. Since this symposium was Hohokam Archaeology yesterday and today, I'm adding a little bit of tomorrow. I thought I would take you through kind of a journey of what the research on the prehistoric irrigation has been in the Salt River Valley. And I'll try to go quickly. I think a number of people have covered some of these points. Prehistoric irrigation is not only important to understanding the Hohokam themselves, it's also important in many other ways, including the canals in the Salt River Valley, showing that that area was excellent for creating an agricultural society. Some of the earliest people that came through the Salt River Valley, Spanish explorers and then later Anglos coming through, noted the canals, including John Russell Bartlett, who headed the U.S.-Mexico Boundary Commission. And they pointed out that, look, this area was under a tremendous amount of irrigation in prehistory. This is an area where we can now start agriculture historically. So a number of the people looking at the canals in the first place were looking toward the future and new irrigated area to grow crops in a new agricultural society. So there were a number of people that took note that these things existed. Frank Hamilton Cushing. I kind of like this shot of him, Dave. Cushing actually was the first not only to do extensive excavation in the Salt River Valley, but one of the first, the first to excavate a prehistoric canal to see what was really going on with these things. He excavated one at the site of El Pueblo de los Muertos, the city of the dead, and it was a canal coming along and it split into two. He excavated the junction and was able to show that there was a series of post holes going across from one canal over the kind of the gore point there, over into the other canal, and show that they were building water control features and really controlling the water in these things. Some of the earliest research was actually focused on mapping the canals. Where were they? How long were they? How did they sit on the landscape? There were a number of people that made early canals. James Goodwin, who was a rancher, he knew where canals were, and for Cushing and the expedition, the Hemingway expedition, he produced a small map of one area of the valley. Herbert Patrick was a professional cartographer. Again, he was very interested in the ancient canals and produced a map of some of the canals. But the first really comprehensive maps showing these systems, their size, their scale, and how they laid on the landscape was a guy we've already talked about, Omar Turney. He was the City of Phoenix engineer and produced a very comprehensive map. His protege, Frank Midvale, actually carried that work on and did a great deal of work for us. This is the Turney map showing the irrigation systems in the valley. Showing how they lay on the landscape. These things are mapped right onto the contours to get exact gradients. So there's just marvelous engineering and intellectual ability of these people. These canal systems are really monumental works of not only engineering but labor. To give you an idea, those of you that know the Salt River Valley, Mesa, Chandler, Tempe, Phoenix, Tolleson, covering about 110,000 acres at its maximum extent. This thing was monumental. It was massive. We've kept up the mapping of these systems. This is kind of the latest iteration of the maps of the valley that I published in 1990, and we need to do it again here soon, update it. There was a lot of mapping going on and showing how these things lay on the landscape, but very little actual excavation work went on until very recent times. There are a few exceptions. Richard Woodbury in the 1950s worked at Park of the Four Waters, the head area of the big system we call Canal System 2, taking off the river at Pueblo Grande. He was looking at them. He kind of got across to people the massive scale of these irrigation canals. They're not little ditches, they're massive. He wrote an article in American Antiquity and another one in American Anthropology on the canals, getting people interested in that kind of research. Emil Howry, seen this picture, at Snaketown, he actually, in his research design, said that he wanted to focus on the prehistoric irrigation. He wanted to know several things about it, not the least of which was what were the earliest canals at that particular site, which of course had already been worked. This was his work in the 1960s, so it had already been worked once. Robert Hershkovitz did excavations of canals when they put through the 60 or the Superstition Freeway, was able to show that we had main canals, we had little distribution canals, smaller canals that came off of the big canals. Was able to show some of the structure. Bruce Massey in Park of the Four Waters, again at the head gates of Canal System 2, did a great deal of work there, showed that there were many canals. Woodbury only looked at a couple, but there were many there feeding that system. Wrote an article that appeared in Science magazine, again generating further interest in these kinds of studies. But I think there was a real change in not only the intensity, but the approach to studying prehistoric canals in the early 1980s with work that was done on I-10 and two big projects there, Las Colinas with Dave Gregory, who many people have mentioned. Also at the site of La Ciudad, U of A and Arizona State Museum did the Las Colinas project, and Arizona State University did La Ciudad. There were some real changes here in our approach. Gregory actually, who was brilliant, in a lot of ways, brought a new multidisciplinary approach to canals. He didn't want just archaeologists looking at these things, he wanted to have other people look at them. So he brought on Fred Niles, who trained me in a lot of ways, who was a geoarchaeologist or a geologist, and he was looking at the sediments in the canals to find out what that could tell us about these particular features. Don Grable has already been mentioned, looking at stream flow and reconstructing the stream flow of the river. They came up with a lot of new ideas about perhaps the collapse of the Hohokam, floods, major floods they identified that may have been problems. At La Ciudad, we did research similar to what was going on at Las Colinas. We looked at some of the elements of the system. Main canals, the big branch canals that carried the water from the river out toward the fields. We looked at distribution canals, the smaller canals that came off. We saw that there were water control features at those junctions. These things are really well controlled and really well engineered. So we learned that. One of the major things that came out of our work at La Ciudad was a long chapter in the report written by Neil Ackerley about looking at historic canals as an analog or an example of how the prehistoric systems may have worked. A really great piece of work that Neil did there. But I think even more important in terms of the La Ciudad effort was that it began kind of a long-term ongoing research effort. We went from there, several of us, and went out and actually started targeting to get projects in Canal System 2 that had canals so that we could start a comprehensive study rather than just looking at the pieces, but get enough pieces to look at the whole. We focused on the elements of the system in some of this early work. No one knew how these things were working. The main canals, how did it get water into the distribution canals? We came up with several different methods that the Hohokam used to manipulate water levels, get it out of the main canal where the water was below the ground surface, get it onto the fields. So we did that. We began to look at how the features operated, how the water control features were built, taking a look at more understanding of the deposition in sediments, which told us things like how they maintained the canals, that they dried them up. cleared off vegetation by burning. We've learned a lot from that. We also came to the realization that canals could, if their capacity and dating is known, how much water they could carry and what time period it was carrying that water. If we knew that, we could reconstruct the evolution of these systems, how they grew through time, and that would be a unique monitoring device for looking at agricultural intensification, more and more fields being planted, more crops being grown, and demographic change, how the population was increasing through time. We also, like many, many other people before us, realized that irrigation has social and political ramifications. That these systems are not just canals in the ground. You have to have a social and political system that's capable of organizing people to run those canals and organize people to build these just huge things. For those of you that haven't seen prehistoric canals, hopefully this will show it up pretty much. You can see here we have one old canal here. It's cut into by this later canal, which is also cutting into another previous canal. We found very quickly that these canals were built, used, abandoned, filled in, rebuilt in a very dynamic fashion. Unlike researchers before us who thought you built a canal and you used it for the next 500 years or 1,000 years. You'll notice Dutch has a very strange grin on his face. That is because we caught him without his hard hat down in the trench. And these trenches you really can't tell here, but they are stepped for safety. But I did catch him and got that grin on film. Another example of a main canal, again, for those of you who haven't seen them, this one's very unusual in that it's preserved on the surface of the ground. These rock lines are the berms of the canal that have eroded. Here's where the canal was going. Unfortunately, this is a little dark in this light here, but this canal actually goes down below the surface these guys are standing on. These aren't small ditches. These are monumental features that they built. And here's another one. You can see the types of sediments that accumulate in them tell us a really great story. Just to show you the most mega canal that I've ever encountered, this canal was at the north end of Dobson Road at the 101 or the 202 freeway. This canal is 15 feet deep, 45 feet wide, and contains 13 individual channels. At one time, this canal was 15 feet deep and 30 feet wide. Try digging that thing out with a digging stick in baskets. We began to look at a number of types of analyses, develop different analytical approaches to understanding the engineering and capabilities of these systems. The first was to use engineering open channel equations. Those are equations that engineers use today to figure out how much water a canal will carry. If the canal is going at a gradient like this, it's this big, it can carry X amount of water. Gave us information on how much water was passing different points in the system. And you can see we targeted projects where we could really get a sample along these things. A couple freeways really helped us in that regard. So we were able to show at this point how much water went through, but what did that mean to the entire canal? We began to look at how a canal changes from its beginning, its head gates, to its end, its terminus. And we found that it actually shrinks in size as it goes from its beginning to its end. But it not only shrinks in size, it does that along a curvilinear fall off. A mathematically precise formula. When a canal is on a certain type of landscape, whether it's historic, prehistoric, big or small, it's going to follow this curve. We found that we had a way of modeling the size of a canal. If I got one cross-section, knew how far that was from the river, I could tell you how big this canal was at any point along its route. That really helps in terms of the archaeology and understanding of what's going on here, because if you know how big a canal is at its beginning and every point in between to its end, you can model it in terms of how much soil had to be removed for the construction of that canal. That gives you a really good clue and idea about the labor. You can play what-if games. What if Canal Grande, the one that was in that other shot, if one person could move 3 cubic meters per day, and we have 100 people working to build that canal, everyone worked every day of the year, we could calculate that out. The Canal Grande would take over 2 years to construct. And it probably took a heck of a lot longer than that because they're not working every day of the year. I don't know about you guys, and I don't work that much. Actually, come to think of it, I do work that much. So we could do that. We could also look at the development of these systems, and they're rebuilding them through time. And we could say how much labor went into building the canal, say, in the classic period. And here's an idea of that. Classic period, Canal System 2, they had to move 846,000 cubic meters of soil to build the system during that period. It took 282,000 person days to do that. So we began to get a pretty good idea that these people must have had back problems. I'll tell you, this was a lot of work what was going into this. We also worked on the other critical component, chronology, developing new techniques to date canals, and work with other dating techniques we had. And when we put together the capacity of the canal and its dating, we can see how that canal system increases through time. It could grow X amount during the, or deliver X amount of water during the pioneer period, Y in the colonial, and we could go like that. Everybody see that? We could see how the capacity, how many acres could be irrigated in each of these periods. So we got an idea of the evolution and how these things actually grew. And it was very different from what people thought. With Canal System 2, people thought up to this point that it increased dramatically through time. In the pioneer period, it's this size, then it would double in size, and then it would triple in size, and then get bigger and bigger. What we found was that isn't true. That these systems, Canal System 2 at least, was built almost to its maximum extent very quickly, probably reaching the extent that could be irrigated depending on the amount of water that could be captured at the head of that canal system. So we began to learn a good deal about how the canals were built, what it took to do that, and how they operated. Then we moved on to, if you will, that's the hardware of the system. We moved on kind of the software of the system, and that is social political organization. What does it take socially to organize people to do something like this, particularly to build and maintain these systems and keep them running? Well, how do you tell from a bunch of relic canals, they're down in the ground, how do you connect that with people? Well, we came up with a way to do that. We looked at how people organized at different scales or different levels of these different elements of the system, how they organize themselves. And here's the lowest level of organization we have. This is a main canal coming down here. Here's a distribution canal. So water's coming off the river into the canal. There's probably a head gate to help regulate water. There are also gates all along these canals we call tap-ons that can stop the water flow, raise levels of water by doing that. And here's the distribution canal. Water is taken off of the main canal through the distribution canal and distributed to, you can see, a whole series of fields. And each of these is a household or a nuclear family field. About 1.8 acres. It matches what we see in the Pima, for Pima families. All of these people have to cooperate to run this distribution canal, to build it, to clean it, to operate it. If everybody along there opens their water control gate at the same time, water levels in the distribution canal go down, nobody gets any water. You have to coordinate water delivery. So this group is a cooperating group, and they're a basic unit of organization to run and maintain the canals. They'll maintain this distribution canal, probably maintain the main canal next to it. And we have a bunch of other levels of this as we go up. We won't go into a lot of detail here, but we were able to show levels of organization at branch canals, at main canals, and this entire irrigation community. And this has already been mentioned, that an irrigation community is a set of irrigation canals that are all interrelated that come off the river in one place. So we were able to show that there's a great deal of organization, the levels of organization to run these things. Some of the other things that we've been doing lately is running computer simulations, running different scenarios. Now with computers getting much more powerful, much more available than they were when I started with punch cards. Anybody do that? Oh, that was a pain. So we have great computer resources now, and we've run simulations based on the mathematics of canals. And one of these I did many years ago. What we did is we looked at it and we said, okay, there's X amount of water coming down the river every year, going back to Grable and his yearly stream flow. Okay, you can probably get this much water off the river and get it into canals. You're going to lose a certain amount to evaporation, to seepage. You're going to use a certain number of acre feet on the canal. And we were able to show basically how much could be produced. We could show how much water could be delivered to fields, how many crops could be grown in those fields, and then how many people could be fed from those crops that are being grown. We could also do that through time, and that's where the important part came in. We found in the early part of the Hohokam sequence, when there weren't a lot of canal systems on the river, they could make a good crop 3 times out of every 4 years. 1 year they'll probably fail because of low flows or something, and they were doing fine. When we see them developing canal systems along the river, they do that up until about 1000 to 1100 AD. They build the last great canal system. The simulations suggest that when they did that, they changed their whole ball game. They stressed their most critical resource, the water. They were using all the water on the Salt River at that point. That occurs right when we see the transition to the classic period of the Hohokam. A lot like what Henry was talking about, it was something, one of those events that really changes society. The platform mounds come in at that point. There's a great deal of change that we see going on. So we can use these computer simulations now to do evaluations of agricultural success. It showed us how the impacts of these floods were, how important storage was, to store enough in case you have problems that you can get over it. And so it showed us a lot of things about the nature of the canals and what life was like for the Hohokam. Just in terms of future research directions, we are continuing a lot of work on advanced computer modeling. One gentleman, John Murray, right? Murray? Is it Murphy? Murphy. John Murphy just finished his PhD, and he assembled a program that will simulate water flow through different segments of canals. And I think he's still working now to apply that to real life, what we're finding in the ground in archaeology, to see a little more about how these canal systems might operate. We need to improve our data collection and secure a more comprehensive sample around the Salt River Valley. We showed you that we got a big sample of Canal System 2. We were able to show its evolution. Recently, we've got a terrific sample of essentially all the canals in the second big canal system there, Canal System 1, and we're hoping to reconstruct the evolution of that system as well. One of the important parts of that project is use of OSL dating. Dating canals is really tough. Just try to go to their door and pick them up for a date. You'll find out. But it's actually very difficult. We do get some ceramics in them, but we have very little in the way of organic material often. And this new technique, optically stimulated luminescence, will give us very, very precise dates. People are always asking me, there's a canal, it's filled in with sediment, it fills in as it's used, and then it has to be maintained or rebuilt. And they always ask, how long did it take to silt this thing in? And my most elegant answer to date is, I don't know. But with this technique, we're getting to the point where we can date things within a very small time period, and we may be able to start understanding the use life of canals, how long they could be used, how long they would last, and that sort of thing, before they have to be rebuilt, and determine some of these rates of siltation. Our big project, we were actually digging canals in the field for over 14 months. We have something like 100 OSL dates, and Dave Abbott and I have a grant request in the National Science Foundation, and we're hoping to get that to be able to do further work. So if you know anybody, drop us a good, So that, I think I'll leave it at that, and we can move on to the next part of the program. How was that for fast? Anybody keep up with it?